Welcome to a new test and teardown video. This time it's some more homebrew equipment. I think this one is a final exams project at a local university, and it's made by 3 guys. I had to remove the names because I don't want to create any kind of problems, but if somebody contacts me and say that they want their names public, I will of course be happy to put them public. So this signal generator is called a Neural Function Generator NE10. And from the front, it doesn't really say a lot about what it's doing. Neuron numbers. So from 1 to 7, you can either add or subtract some signal to an input-output signal path, or you can do nothing if it's in the middle. And of course there is an input attenuator, so if it's 1 or 10 volts, the input signal. So I think this unit is doing some mathematical functions to a signal in more or less real time. I will show you what is inside so you can see all the cool details. So the power supply is just super normal kind of stuff. Plus minus 5 volts and plus minus 15, or no, it's plus minus 12. And then we got the entire front end here, and that is completely analog. It looks like we got some transistors and stuff here, but if you look on the nicely Neuron plug-in boards, you will see the CA3083 from about the year 1990. So they consist of 5 transistors each. So it's just a transistor array, and that's all it takes to do the add or subtract of analog signals. See, they home design, home etched and drilled and soldered all the PCBs like that. And then we got 2 more. There's this, if you look at this circuit here with the resistors and the 2 ICs, it looks a lot like this unit. And of course you'll see that we got 7 identical plug-in modules and then 1 that's always here, and that is something I will explain in a second, because we got 7 plus 1 makes 8 in total, and the first one you just can't disable, it's always there, right? So that is the main idea. So let's look at the brain inside this unit. I probably need to put it like this. So let's look a little bit on that PCB. See, here is an 8-bit interface port to a PC parallel port, or probably another master microcontroller board or something like that as well. It's hard to guess exactly what is going on here, but so the 8-bit port goes to 2 latches. So those 2 are 8-bit latches with output enable always on, and then the strobe signal to each of the individual latches just go to 2 individual bits in this flat cable. So that means you can set up 8 bits on this one. This one I will call the DA converter latch, because all the 8 bits from this latch only goes to an 8-bit DA converter. And then the analog signal from that one goes to the op amp, and then some trimmers, and then the output of the op amp goes in parallel to 3 8-port sample hold circuits. So there are 8 output, 1 analog input, and then they will store the analog input to each of the 8 outputs depending on the channel you are pointing to with the control latch. So 3 of the bits from the control latch goes to select one of the 8 outputs of this, that, or that one. And then we got 3 more bits, I call it bit 3, 4, and 5, in the control latch that strobes or store the output of this, that, or that one. So you actually got 24 analog outputs in this flat cable. So 24 analog outputs can be set up to be constantly active at the same time. And since there is no clock or anything between those 2 boards, yeah, you just have analog outputs going in here. Now look at this. 3 analog signals. I don't know if that is possible to see on the traces here, but 3 analog signals goes to each of the 8 channels. Of course, 3 of them also goes to this one. So that is, of course, the non-modified, the positive, and the negative signal, as far as I can imagine. And then it's just added up in the transistor circuits on each of the different boards. And with the switches, you can simply enable or disable the positive or the negative signal that's already generated by the sample hold or the analog channels if you want. So I think it is a very, very complicated final project to do, and especially the software you know, they used to do this. Oh man, that's probably quite complicated. So this is the 8-bit port connector, and this is the data structure of that connector. So we got 8 bits of data going into the 2 latches, and then we got strobe for the ADC latch, and it's a high to low transition on the strobe signal, and then that latch stores the 8 bits. And then we got a control latch, and then we got the sample clock. That sample clock goes to 3 pins of the 74LS00. That's the 4 NAND gates right there. And it looks a little bit like this schematic here. So this is the sample clock signal. And for this to work, the inhibit signal is actually the store signal of the 3 sample hold ICs, and they look like this. So this is the inhibit store signal that needs a low transition, and that will be the first 3 bits of the control latch that selects which one of the 8 outputs we're storing this analog input at, right? And then that will be the next 3 bits, right? Latch bit 3, 4, and 5. That it kind of enables that clock signal to go to that sample hold chip. So that is how I will try and wire this up. I'll use an Arduino, and And here is my little Arduino experiment. So that is my 8 bits. I use this port and this port, and then my 3 control signals. I like to leave RX and TX free, especially because they are wired to the programming interface of the Arduino. So I could corrupt the bootloader from uploading if I'm using RX-TX. So that's my idea on this. And then I should just plug in my little interface, and then hopefully write a little piece of software for this. So now I'm ready to test this unit, but when I power this unit up, I see a power consumption of 65 watts. Are you kidding me? So something here gets red glowing hot. So I will immediately turn off power, and it is the main transformer. Oi, this is red glowing hot. So there's something here that is shorted. Oh man, so this is going to be a repair job first. That sucks, because I really wanted to play with the software thing. So I just took out the power supply, and I really would like to tell you not to do this. Please don't solder on wires you want to put into screw terminals. Here we got screw terminals for everything. Because if you solder on wires you put into screw terminals, after a little while, the solder is going to like reset itself, because it's under pressure, so it's just gonna move slowly away from that pressure, and then your wire is gonna get loose. So half of these they were like really loose because of that. So that is wrong and a bad way to do it. Here's your ground. So this product here is using chassis as ground, and I was using my thermal camera to see about what is going on here, and we got 2 shorted diodes. So we got 4 diodes here in this rectifier bridge on the secondary side, and 2 of them, they are shorted. Probably something else is shorted too, but I think I want to change the diodes first. Also, I'm not super happy about using protoboard for mains entry. Okay, they did remove the copper just in between here, but they didn't do it out here and stuff like that. So this is not super good for isolation. So I found the bug, and it was not the diodes. I really thought it was the diodes, but those 2 diodes make the negative supply, and the negative supply goes to one of those capacitors, and it was just completely shorted. And the other one for the positive supply was not shorted, but of course I changed both of them, so they're now nice and new. Because if one is shorted, then of course the other one would be shorted too soon. But now the power supply is running, and it's only using 2 watts, and I got all the voltages out here: -15, -12, +5, and +12. So now I will assemble the unit again. So my very first try actually works. This is my first upload of my Arduino code, and all I do here is I just ramp, I just count up to the DA converter, and then the output of the op amp go to the input of the sample holds, and here you go. It's just counting nicely up, and it's nice and linear. So that means now I can continue with my little software here to write to the control latch and hopefully get outputs from the different sample holes. Just wanted to show you what I've been figuring out here. So what I'm doing now is I'm generating the same sine wave on all 24 outputs that goes to all this add subtract system here, right? So with all the switches in the middle, the green signal here is the output. So now I can add more and more of them, and then I get this funny signal. And of course, if I subtract some of them, the signal goes down like that. That is a little bit funny how it looks. So I've been playing around with the software, and the setup is of course not meant to be done by humans, but of course by a neural network that will put in the parameters to generate whatever kind of frequencies or any kind of curves, shapes or forms from whatever kind of input signal, and then it can merge the neural generated add subtract features. But it's super fun to play with, and definitely something that I will spend a few days playing around with. At the moment I'm running with 24 DC levels, so now I can definitely control all the different sample holes, and all my analog signals goes exactly as they're supposed to, and by changing the different parameters here, I can see that I'm affecting my incoming signal. I will put a link to some more information about this stuff, so you can read a little bit about it if you want. So I would like to say thank you very much for watching. See you. Bye bye.